We will move on to the inertial gravity waves and mixed Rossby gravity waves in a minute, but let me close out this part of the equatorial Rossby wave by looking at the longitudinal scale and its response to the basic state. So if you look at a westerly basic state and look at some small longitudinal scale, longitudinal scale, relatively high zonal wave number. This is again something you have to just get used to. So ER latitudinal structure in zonal flows for zonal wave number of -3, -5 and -9. So now you know why we are writing Ka instead of just K. K is just kind of logically set to the equatorial wave numbers, whereas Ka allows you to have meridional structures which are off equatorial, so there is a latitudinal dependence as well. So look at the easterly basic state for n equal 1 and different wave numbers. So obviously as the wave number increases, the longitudinal scale decreases. So you can see that the equatorial trapping or the meridional structure changes here, going from -3, which is at somewhere here. Not a big change, but you can see the depth. Sorry, what's on the vertical? This is just the amplitude of the meridional mode. So you can see that the amplitude drops for higher wave numbers, which is makes sense, right? So that's the stationary state, which is somewhat similar. But when you go to westerly basic state, you can see that there is a massive change in the meridional scale of the wave, depending on the wave number. The -9 here, westward wave propagating equatorial Rossby wave with wave number 9 is going all the way to the poles for the first meridional mode. Okay, so you can see the same thing here in terms of latitude and the depth dependence. Again, the basic state being stationary doesn't make any difference, but when you have westerly regime, you have a switch from positive here to negative, which is going to produce unrealistic solutions, as we will see later on. Whereas if you have, these are both marked positive here, so again some error, so we will not bother too much with this. But just remember again that the assumption we made about the basic state can affect the solutions, because to get easterly or westerly flow basic state, we need a geostrophic balance, which means that slope of the surface HS we assumed is going to fail us when you have certain wave numbers and certain basic states. So not all solutions are possible, essentially, which means there are normal modes, doesn't mean all the normal modes actually occur. Okay, so the let's see, let me make sure I didn't miss anything. U bar greater than 0, latitudinal scale of the modes increases substantially. In B, the variation of total depth for various basic states. In a quiescent basic state, the depth is constant, the black flat line we saw. In the easterly basic state, the fluid increases depth with latitude in order to support the geostrophic state. However, with the westerly basic state, the fluid possesses negative depth at near 55 degrees. So basically the assumption we made about the fluid depth and the geostrophic flow of westerly plus 10 meter per second is not going to work in terms of the slope hitting the bottom at 55 degrees latitude. So looking at the inertial gravity waves, which have the westward and eastward phase speeds, high frequency equatorial, these are high frequency equatorial waves trapped, equatorially trapped, and are an important phenomena in the tropical atmosphere, taking part in the geostrophic adjustment to forcing this when the scale of the forcing is less than the equatorial Rossby radius. So depending on the forcing is going to perturb the system. Then these waves that radiate out from the forcing, depending on how large it is compared to the Rossby radius of deformation, the equatorial Rossby radius of deformation, we want to see how quickly the system comes back to geostrophic balance, right? So inertial gravity waves basically determine that. They radiate out the perturbation and bring the system back to geostrophic balance. So consider the high frequency limit, where the frequency of the wave is much larger than the inertial frequency of the Coriolis in the dispersion relation that we looked at before. Which we then we get this relation, which is rewritten in terms of the dependency on meridional mode and the background state or the basic state. So mixed Rossby gravity waves then in the frequency domain, they have n equals 0, right? It's like a Fourier transform. The dispersion relation for the MRG can be written as, okay, in this relation we're going to set n equals 0. We get omega d squared over c squared minus k squared equal this term equals this term. So you know that this is again a cubic equation. So we got that by setting 0 here. That's what I'm showing. You can now plot that relation in terms of westward mixed Rossby gravity wave and the zonal number and frequency. So the same diagram we saw for all the waves, we are now splitting into individual eigensolutions. We did the Rossby wave, which is very important for all the low frequency processes, and in the ocean also for short Rossby waves or high frequency, and wave numbers, right? So again, the main message, it's n equals 0, of course. Dependence on depth, we are setting 300 meters here. The dependency on depth is not great for the Kelvin and mixed Rossby gravity waves, especially at high frequencies. But you can see that the difference also for the background basic state is not that great when you look at the dependency on of the wave number and frequency on the basic state. Okay, I hope I'm saying it clearly enough for you. Just make sure you understand. Okay. Looking at the zonal group speed, they are all positive in this selection we have made with the depth and wave numbers. So you can see that as the low frequency, as you approach lower wave numbers, which means longer scales and lower frequencies and dependence on equivalent depth, the group speed increases. Okay, so what is the message? For, let's say you fix the wave number, as the equivalent depth increases, the zonal group speed increases. Okay, that is consistent with the idea of the equatorial trapping. So if you pick a particular wave number, zonal wave number of -8, particular equivalent depth for the mixed Rossby gravity wave, you can again see the impact of the background state. Main message is not as dramatic as for the equatorial Rossby waves. So this is for the zonal wind, this is for the meridional wind, and this is for the geopotential. So that's something you have to remember. Okay. So variation of the eigenfrequency, I'm not going to read the caption. I already said everything that needs to be said. Okay. So as with the equatorial Rossby modes, the latitudinal extent of the mode is greater for positive U compared to negative U bar. So westerly flow tends to expand the equatorial trapping latitudes for the mixed Rossby gravity waves as well. Let me come back to the Kelvin wave, which is also a really important wave in the system in the next podcast.